Hello, this paper presents the performance evaluation of saturating Class C driver circuit for inductive wireless power transfer. The authors of this paper are Mohammed Karam Moni Rabby, Shamim Ara Shawkat, and Mohammed Shah Alam. This research was conducted at Bangladesh University of Engineering and Technology, in short called BUET, Bangladesh, in collaboration with the University of Tennessee. I will walk you through the following key sections: an introduction to wireless power transfer, in short called WPT, its background and applications, advantages and challenges, our proposed system block diagram, the circuit design technique we followed, simulation results, and finally our conclusions. At its core, inductive WPT is based on electromagnetic induction, allowing power transfer without physical connectors. It involves a transmitter with a primary coil and a receiver with a secondary coil. When alternating current flows in the primary, it generates a magnetic field, inducing a voltage in the secondary to power the load. The visionary Nikola Tesla pioneered this concept in the early 1900s. His experiments at Wardenclyffe demonstrated wireless lighting over 25 miles using high-frequency currents from Tesla coils, laying the foundational principles for resonant inductive coupling we use today. Later, in the mid-20th century, research shifted to microwave-based WPT, notably by William C. Brown in 1964, who created the rectenna to convert microwaves to electricity. While effective for long distances, these systems face challenges in efficiency and safety. WPT saw a major revival in 2007 with MIT's ICECE project. By using resonant coupling at 9.9 MHz, they wirelessly powered a 60W bulb 2 meters away with 45% efficiency. This proved that resonance could enable efficient energy transfer over greater distances and with more flexibility. WPT has diverse applications. In biomedics, it powers implantable devices like pacemakers. In consumer electronics, it enables cordless charging for phones, vehicles, and home automation systems, creating seamless and integrated power networks. The advantages are clear: increased reliability by eliminating battery swaps, greater convenience with no cables, and environmental benefits through reduced battery waste and energy loss in conversion. However, challenges remain, primarily in improving efficiency, expanding product diversification for wider adoption, and navigating regulatory issues around safety and standardization. This is our system's high-level block diagram. A DC source feeds a Class C driver, which energizes the primary inductor. Power is transferred inductively to the secondary, rectified, and delivered to the load. Our design followed a structured approach: first, defining geometry and magnetic constraints; second, the magnetic design of coils; third, the electronic design of both primary and secondary circuits, including the Class C driver; and finally, control simulations to validate performance. This flowchart details our iterative design process for the secondary side. We match the secondary coil to the load, calculate equivalent AC parameters, select components for optimal quality factor, Q, and iterate until link efficiency is satisfactory. Here we see the Class C driver's switching operation. A key innovation was selecting a single MOSFET, the SI4490DY, instead of two in parallel. Its high drain source voltage rating and low on-resistance strike a balance between robustness and efficiency. Similarly, the primary design involves calculating driver parameters in function of the primary coil, optimizing for efficiency, and iterating based on measured quality factors. SPICE simulations were used to validate the design before implementation. For validation, we designed a test system, a telemetry unit powered wirelessly over 70 mm, consuming 4 mA from a 4V supply. Key parameters include a 1 MHz operating frequency and a coupling factor, K, of 0.71%. Simulation results show stable output, nearly 3.85 V DC and 3.42 mA DC at the load with minimal ripple. The waveforms indicate clean power delivery suitable for sensitive applications. Our efficiency results are promising. The driver efficiency reached 90.34% and the link efficiency was 8.5%. The overall system efficiency was 5.65%, a significant figure given the constraints of small-scale, biomedical-style WPT. Compared to an existing driver using parallel MOSFETs, our single MOSFET design shows clear improvements: higher output voltage and current, boosted driver efficiency from 83.8% to 90.34%, and a major jump in overall efficiency from 1.7% to 5.65%. In conclusion, we achieved a significant improvement in area efficiency using an optimized saturating Class C driver. Future work will focus on further efficiency enhancements and addressing regulatory coordination for practical deployment. Our work builds upon foundational texts and recent research in inductive power transfer, cited here. We especially acknowledge the work of Van Schulenburg and Pewers. The development of the performance evaluation of saturating Class C driver circuit for inductive wireless power transfer is an ongoing process, and we welcome any suggestions or insights. If you have any questions regarding this work or are interested in collaborating on future research in this area, please feel free to contact the authors via the provided email addresses. Thank you for your attention and interest.